So we're talking about electrode potential. Okay, as we mentioned, it's a topic that may seem really complicated, but if we interpret it in our own way, we can make it very simple. There are just a few things to understand. One is that we're given a list of half equations. These half equations are always given as reduction. Yeah, in fact, the electrons, notice, are on the left-hand side of the equation, like this written on the screen. And then we have some values. The unit is voltage. They can be positive and negative, and the hydrogen is always zero. And that's called the electrode potential. What is helpful to then understand the logic behind these numbers and really their meaning is to understand the meaning of electrode potential. Because what it is, it can be explained in a difficult way, like it's a kind of force, but just think it as like, if we keep it simple, as the tendency or the ability of one element or ion, yeah, to gain electrons, right? Because it's reduction potential, so we're referring to gaining electrons. And then I want you to think about what that positive and negative means. So that's the first thing, the definition. So this ability to gain electrons, let's keep it very simple. So if it's positive, think about it, the ability to gain electrons, what do you think it means? Well, it's more able to gain electrons. I also like to think it is this way, just to keep it a bit more visual. You're talking about electricity at the end, isn't it? It's like the potential, voltage. It's all about moving of electrons, electricity. If it's positive, means that more electrons flow to it, right? Because more electricity. If it's negative, the electrons will flow away. So the electricity is moving away from that element. So the important thing to understand is electric potential is this tendency of gaining electrons, because it's reduction potential, so gaining electrons. If it's positive, it's more likely to gain electrons. If it's negative, it's less likely to gain electrons. So we have three examples here. We have three equations. Fluorine gains 2 electrons to form the fluoride ion. It's very positive. So this means that it's more likely to gain electrons. So this will be most likely to be reduced, because positive, more likely to gain electrons. Negative, we have lithium in this case, it would be more likely to lose electrons. So despite this being given as a reduction potential, if we consider these two equations together in a redox, the lithium, it's very negative. It's not so likely to be reduced, but it's more likely to be oxidized instead. So one step back. The values tell us what's more likely to be reduced and oxidized if we look at combining two elements together, because at the end, the redox explains chemical reactions, like why actually things react together, okay? But the value also tells us which one is more likely to be reduced or be oxidized. So if we combine two half equations, then we can predict which one is reduced and which one is oxidized. But before we look at that, I want you to, oh, what's happening? Sorry, I didn't want to delete everything. I want you to think about the concept of reducing oxidizing agents, okay? Of course, it's always like relative to two elements reacting together. So if fluorine is very positive, as we said, it's more likely to be reduced. Guess if it's a stronger or weaker reducing or oxidizing agent. So the more positive it is, the more likely it is to gain electrons. Gaining electrons means reduction, so will be the strongest oxidizing agent. So as we go down the reactivity series, we have at the top the strongest oxidizing agent, at the bottom the weakest one. But it's opposite the truth about reducing agent. Let's think about lithium. Lithium is very negative. It's more likely to lose electrons. If it loses electrons, it's oxidized. So which agent is reducing? So notice that I really don't want you to try to memorize this. Just think it with logic from the basic of the definition, understanding the movement of electrons, so in terms of oxidation and reduction, and then you can figure it out if it's a stronger or weaker reducing or oxidizing agent. But if we want to make a note, at the bottom of the electrochemical series, we have the strongest reducing agent, or the more negative is the strongest reducing agent, while at the top we have the strongest oxidizing agent, yeah, at the very top. Then another part is, think logically. In this case, it's simple because we have fluorine and we have lithium ion. Fluorine is more likely to gain electron, isn't it? It's a non-metal. Think about the basic of chemistry that you know. Lithium, well, it's a metal. What is more likely to do? It's going to be more likely to lose one electron. So actually, in this direction, the equation, rather than the reduction equation. Okay, so take a moment to think about this. I've added the hydrogen there because everything, so those are called the standard electrode potentials. So they are measured as this tendency to gain or lose to gain electrons as reduction potential relative to hydrogen. So hydrogen, it's zero, the electrons don't move, but the electrons either move away or towards the second cell. And here I invite you to look at diagrams in your book about the electrochemical cells, how they're set up. Yeah, so we have normally two beakers with the electrode, okay, and then just have a look experimentally what that looks like to kind of visualize better the flow, okay? It's a bit simpler when we have like a metal and a non-metal because we can kind of guess the transfer of electron, the direction. A bit more complicated is if we're comparing, for example, true reduction of metals. Now, thinking what we said before about definition of electrode potential, the meaning of the negative value, more negative, more positive, what it means in terms of like oxidizing, reducing agent, I would like you to take a moment to think about between these two, which one would be reduced and which one would be oxidized, or find the reducing and oxidizing agent. Okay, because the goal is to combine these two equations. Of course, one will be reduced and one will be oxidized to have an overall equation. Try. So Zn, let's do the thinking process together. Zn2 plus, yeah, to zinc solid, minus, so it's more negative than the iron. More negative means more likely to be reduced. So good. This is the one that would be reduced. Or this would be the oxidizing agent. Mm-hmm. Very good. The second one, it's less negative. So let's say more positive. Oh, or is the other way around? It's a bit more difficult when we have two negatives. But if it's more negative, the electrons are more likely to flow away. So actually, oh no, everything got deleted. It's the opposite way around. Okay, let's try again. If the Zn is more negative means that it's less like the electrons will flow away. Okay, remember electricity flowing. So more positive means gaining electrons. Less positive means losing electrons. So despite both being negative, one would still be more likely to gain electrons. And that would be the more positive, which is this one, it's iron. This one is more likely to be reduced. Or better, is the strongest between these two oxidizing agent. Why? Because this is more positive, even though it's negative. So it's hard, yeah, it's confusing unless you really, like the logic thought, it's clear. So that's why it's important to try it out like this, like very logically. Let's do the same thing for the first one. Zn2 plus, so this is more negative. More negative means, yeah, then you can think it in your own way if it's like more like the electrons flow to it, or strongest reducing oxidizing agent, whatever makes sense to you. For me, I need to go very slow in the explanation. It's more negative. What does that mean? It means that the electrons will flow away. It's more likely to be oxidized. So this one will be the one that is oxidized. So it's the strongest reducing agent. Or let's just write it as the weakest oxidizing agent. Instead, we want it to be the reducing agent. But let's stop a moment here. They're both reductions. We can't combine them like this. Guess which of these two equations we will have to flip to make oxidized. The first one is being oxidized. This means that the first equation, the more negative one, is not going to be a reduction equation. It's going to be an oxidation equation. So it will be like this. I ignore the step symbols now, doesn't matter. So zinc, it's more likely to be oxidized and not reduced simply because it's more negative. And then we have this other equation, it stays as reduction potential, like this, like as a reduction. The values don't change. Very important. But we will see what changes. Yeah? We combine them just as we usually do when we have two-half equation and we want to get the overall equation, which is by canceling out electrons. Notice that now they can cancel out because they're on opposite side. So to form the overall equation, it's very simple. We don't need to time anything. We don't need, yeah. So it's going to be like that. But now I want you to think about how do we find the electric potential of this whole cell? The cell is when we have these two, like the two reduction, like the two equations, reacting together. We can find the cell potential, it's called. For me, it's very simple to think it as, well, you flip around the first equation because that's not reduced, it's going to be oxidized. We saw it's more negative, it's going to be oxidized. So guess what happens to this value? This is the one that will have to change sign. So this will be, so the equation would be minus 0.44 plus 0.76. And this will give you the electric potential. Yeah, so 0.32 will be your positive value for this cell. Okay, so to summarize, the value of the electric potential tells you about the strength of oxidizing or reducing agent. Okay, it's important that you find your own way to explain it. Okay, for me, it's simple to think it as the more positive, the more likely to gain electrons. So if you have two equations, yeah, to combine, yeah, if you're looking at the reactions, for example, of two metals and they're both negative, you need to think about the more positive and more negative value. The more positive means it's more likely to gain electrons, so will be the strongest oxidizing agent. That's why it will be the reduced one. But this means that the second equation will be not reduced, but will be oxidized. So when we want to construct a redox reaction, one of them will have to be oxidized. So that's the one that you flip around. And to find the overall value, we actually need to change the sign of the one that is oxidized, which is the one that you flip around. Okay. In the book, sometimes it's written a bit more complicated, like, yeah, the one on the left, the one on the right, could be a bit more complex. This is the very, very simplified explanation. So I would suggest you after this, maybe go and read your book, go and read some other notes and see if they make, if they make a little bit more sense. And if you find it your own way to understand it.